Today, we're going to demystify the completely invisible, yet totally fascinating world of thin film coatings. We're focusing in on a truly remarkable technology called physical vapor deposition, or as it's usually called in the industry, PVD.
So think about this for a second. How exactly do we manufacture the complex, high-tech objects we rely on every single day? We're not just stamping out plastic or molding metal here. For the really advanced stuff, we are literally building them from the ground up, atom by atom. To figure out how that works, here is our agenda for today. First, we'll define what PVD is. Second, we'll break down the three-step process. Third, we'll look at why vapor deposition works so well. Fourth, we'll talk about the strict vacuum requirement. And fifth, we'll cover the 5 main types of PVD.
All right, let's jump right into Section 1. What exactly is PVD?
At its core, physical vapor deposition is a family of thin film coating techniques. It's actually a pretty logical concept. You take a solid piece of material, physically force it into a vapor, and let that vapor settle onto a base material, which we call a substrate, to form a brand new solid film. And the key word here is physical. Unlike chemical processes that rely on complex reactions, PVD relies entirely on physical mechanisms like intense heat or energetic impact to produce these insanely high-purity, perfectly controlled thin films.
Now, this might sound like deep, abstract atomic science, but you actually interact with PVD technology constantly. It's what makes the microelectronics in your smartphone and laptop possible. It coats the optics in your camera lenses and anti-glare eyeglasses. It's used to harden the cutting tools in heavy manufacturing, sometimes extending a drill bit's lifespan by up to 10 times. It even gives you those sleek, incredibly durable decorative finishes you see on high-end watches and modern hardware.
So how does it actually happen? Let's move to Section 2. The three-step process.
The entire mechanism of PVD basically breaks down into 3 distinct logical steps. First up is generation. A solid target material is violently converted into vapor using either raw thermal energy or energetic particle bombardment. Step 2 is transport. Those freed atoms travel through a highly controlled, low-pressure environment. And finally, Step 3 is condensation. Those traveling atoms land on the substrate, cool down, and condense to form a perfect, continuous thin film layer.
Which naturally brings us to Section 3, why vapor deposition works. You might be wondering, why go through the immense headache of vaporizing solid metal in the first place? Well, because the payoff is massive. Arriving as a high-energy vapor allows the atoms to bond beautifully with the substrate, giving you incredible adhesion. It also lets the coating wrap uniformly around highly complex 3D shapes. You get stunningly pure films because there are very few contaminants in the mix. And honestly, the most impressive part? Engineers get precise thickness control right down to the nanometer scale.
Think about what that level of precision actually means. When you are building up a surface layer literally atom by atom or molecule by molecule, you are granted unprecedented, ultimate control over the final material's microstructure. Engineers can literally dial in the exact mechanical, optical, or electrical properties they need just by changing how those atoms stack up.
But you can't just do this out on a table in the open air. That brings us to Section 4, the vacuum requirement.
To give you a real sense of scale for the engineering challenge we're talking about here, PVD systems have to operate at incredibly low vacuum pressures. We are talking ranging from 10 to the -2 all the way down to 10 to the -7 millibars. To put that into perspective, we are basically simulating the vacuum of deep outer space right inside a box on a factory floor. And this intense vacuum isn't just a technicality, it's absolutely critical. First, it minimizes collisions. You want those vapor atoms to travel freely from the source to the target without crashing into random air molecules and scattering off course. It also actively strips out oxygen and water vapor, which prevents contamination. By totally removing those impurities, the final film reaches peak purity, and it guarantees that engineers get a perfectly reproducible result every single time they turn the machine on.
Okay, so how do we actually do this in practice? Let's check out Section 5, 5 types of PVD.
Material scientists basically have a menu to choose from here. They rely on 5 main techniques, and they pick the right one based on the specific material they're vaporizing and the exact finish they need for the final product. Let's run through these individually. First up is thermal evaporation. It is exactly what it sounds like. The solid target material is heated up, either resistively or by blasting it with an electron beam, until it literally reaches its boiling point and evaporates. It's a remarkably simple, cost-effective method, and it's perfect for materials that naturally have relatively low melting points.
Next, we have sputtering. Instead of just heating the material, this method uses high-energy ions, usually generated from a plasma, to aggressively bombard the target and physically knock atoms loose. This category includes variations like DC sputtering, RF sputtering, and the huge industry standard magnetron sputtering. Because of the sheer kinetic energy involved, it works exceptionally well for complex alloys and compounds, and it gives you much better uniformity and adhesion than basic thermal evaporation.
Number 3 is pulsed laser deposition, or PLD. Here, a high-energy laser pulse directly strikes the solid target, instantaneously vaporizing the surface material. If you are working in advanced materials development or high-level research, and you absolutely need highly precise, stoichiometric films, this laser-driven method is going to be your go-to tool.
Fourth on the list is cathodic arc deposition. By utilizing a literal electric arc, this method violently vaporizes material right off a cathode. This creates a highly ionized vapor that results in incredibly dense, strongly adherent coatings. Because it creates such a tough film, it is super common in the industry for applying hard protective coatings, like titanium nitride, onto manufacturing tools to make them last longer.
Finally, we have ion plating. Think of this as the ultimate hybrid method. It essentially marries the basic technique of evaporation with a simultaneous, continuous ion bombardment. This 1-2 punch dramatically improves the density of the film and its adhesion to the substrate. It's incredibly useful for applying coatings that require deeply enhanced mechanical durability.
But whether you are boiling metal with an electron beam or blasting it with plasma, the core story of physical vapor deposition always remains exactly the same. It is all about transforming a solid into a vapor, carefully transporting it through a deep vacuum, and letting it condense to form flawless, microscopic layers.
As we wrap up this explainer, it really leaves you with something to think about. As nanotechnology, microelectronics, and material sciences continue to rapidly advance, how will these invisible atom-by-atom processes continue to shape the manufacturing, the durability, and the sheer functionality of our modern world? The next time you look down at your scratch-resistant smartphone screen or put on a pair of anti-glare glasses, just remember the incredible atomic journey it took inside a vacuum chamber just to make your life a little bit easier.